So we'll start chapter 11, which is angular motion. So under kinetics, under kinematics, we have chapter 11 called angular motion. So let me write. Angular motion. Well, there is not much of a theory in this. There's not much of a new theory in this. It's basically an extension, or you could say an analogy. You could set everything in an analogy with linear motion. For example, we have looked at the formulas in linear motion. The formulas we have looked at are, let's say, as a definition of acceleration, we have said v equals u plus at, right? Or in other words, v equals v naught plus at. Okay, I've used v or e or u or v naught for initial velocity. So let's make that clear here. These two are initial velocity, of course final velocity, and a is acceleration, right? And then we said s equals ut plus half at square, and then we have said v square minus u square is 2as, or v square minus v naught square. Doesn't matter, it's the same formula. You can use any nomenclature as long as you understand that these terms are initial velocities. Alright, so all of this was for linear motion. In angular motion, we have an exact same thing. We're just changing the terms. Okay, we'll say omega equals omega naught plus alpha t. Okay. Once I give you the formulas, then I'll go into the explanation of what each of these terms means. Okay? And here theta equals omega naught t plus half alpha t square, and then here we have omega square minus omega naught square equals 2 alpha theta. If you look at these sets of equations, you will easily see that you will see the correspondence between the linear and the angular motion, right? This is linear, this is angular. Okay. So in linear motion, things are going, obviously, as the name suggests, in a straight line. Okay. In angular motion, things are rotating, right? Things are, you could have an arm that is pinned, and this is rotating. Okay. Or a shaft that is rotating, right? You can have a shaft that is rotating, right? You could say this is rotating at certain RPM. So the same formulas apply in both cases. Here, what is distance is given by, in the formulas, s. Here, instead of distance, you have theta. Right? Angle. theta. So here you will say how much distance has something traveled, or how much displacement. Here you will say how much angle has it covered, right? If this arm is turning, you will say, okay, if it has gone through 2 revolutions, then we'll say how much angle. So it would be 360 times 2, 720 degrees theta. So that is the correspondence between the linear and the angular sides. Okay, here we have said velocity. Okay, velocity, either u or v naught or v, right? So this is, we have said initial, and this is final. Okay, here we'll say angular velocity. Angular velocity is omega naught and omega. Okay, here unfortunately we have to go with subscript. We don't have much of an option. The conventional the convention is in most of the books is to go with omega naught and omega, whereas in the linear side the convention is either u for initial velocity or v naught for initial velocity. Okay, as long as you in the formula, like I've mentioned this before, in the formula, don't memorize the formula based on uv, memorize the formula based on initial velocity, final velocity, acceleration, distance, etc. Okay, here we have acceleration is, we have said either a, or if gravity is involved, we have said g. Okay, here angular acceleration is alpha. Okay, is alpha. That's all. So if you take any formula that deals with on this side, if you take any formula on this side, we can just substitute these and get the formula for the angular side. Like if we have s equals ut plus half at square, here we'll say theta equals omega naught t plus half alpha t squared. Time, thank goodness, is time in both cases. There's nothing different about time. So that's a constant. That doesn't change from one to another. I shouldn't say it's a constant, but it doesn't change from the linear side to the angular side. Okay, v square minus u square is 2as. Omega square minus omega naught square is 2 alpha theta. Sorry, 2 alpha theta. Did I write alpha as, yeah, 2 alpha theta. And then v equals u plus at, omega equals omega naught plus alpha t. So these are the formulas. Based on these formulas, let's do a problem. So this is problem number 11.9, I believe. 11-9 in your book. I'm going to read the problem out. Starting from rest, a shaft accelerates uniformly to 800 rpm in 10 seconds. Determine the angular acceleration in radians per second. Okay, starting from rest, so omega naught is 0. Okay, the shaft accelerates uniformly to 800 rpm. So omega, final velocity, is 800 rpm. Okay, in 10 seconds, time is 10 seconds. So we're asked to find what? We're asked to find the acceleration, the angular acceleration. So alpha is what we need to find, and we need to find this in radians per second square. Oh, here, sorry, I didn't mention the units. So for s, it is theta, so that's in radians. Okay, omega is radians per second. Alpha is radians per second square. Okay? All right. Now we know that 2 pi radians, 2 pi radians is 360 degrees, right? So we're going to use that as a conversion factor. A lot of times in all of these problems, the question is given in terms of either degrees or either RPM. RPM means revolutions per minute. So we have to always convert that to radians. So radians per second. Okay. So 800 RPM means what? So this shaft here, okay, is turning 800 revolutions in 1 minute. Now one revolution is 2 pi radians, right? One revolution is 2 pi radians. So 2 pi, so 800 revolutions would be 800 times 2 pi radians, right? And minutes will convert that to seconds. So first let's do this, and this is going to be a common theme in all these problems. You would have to convert RPM to radians per second or vice versa. Okay, so you should be pretty fluid with this conversion. Okay, so 800 RPM, right? I'm going to write this as 800, right? Revolutions per minute, right? So times, then we say a minute is 60 seconds. So you have done this conversion. If minutes is here in the denominator, we want minutes in the numerator, 1 minute, and we'll say 60 seconds. We want it like this so that later on we can cross them out. Okay, and then revolutions. So revolutions is in the numerator here, so we want it in denominator. So 1 revolution is 2 pi radians. Okay, and now we'll cancel everything out and we'll see what it means. So revolutions cancel out. Of course, minutes and minutes have cancelled out. So 800 times 2 pi divided by 60 radians per second. So if you calculate that out, it comes to 83.8 radians per second. Okay, this is the omega. This is the final velocity. So we have initial velocity, final velocity, time. So we're asked to find acceleration. Now on the side, you can always kind of, you can always say v equals u plus at. Then you can say omega equals omega naught plus alpha t. So you can do this on the side, and then just so, because you've had practice with this up to now, and like I said, all it is just changing over from linear to angular. Okay, so if we want acceleration, so we do omega minus omega naught over alpha, over t. Okay, so that would be what? What does that come to? Omega is, we have 83.8 minus 0, omega naught is 0, divided by 10. 10 seconds is the time we have. Okay, so that's 8.38 radians per second square. Okay? So that is the angular acceleration.